record. Okay, so presumably we're recording on this computer. I don't know what this thing about polls is. Let me start chat going. Okay, so mainly questions. Does somebody have a question? By the way, I'm going to connect the now I've got the iPad connected. Wires are tangled. So swipe to open, notes. Boy, this is taking a while. Okay, so once again, this, yes. Okay, well, there's an interesting question, Runge-Kutta. I tell you what, I will think about that and discuss it in a future class, but I have not studied Runge-Kutta in detail ever, and I think it's built into routines that are available in MATLAB and Sage and Mathematica and so forth. But I may have studied it, but in any event, I forget how it works. But what is true is that these things generally are, so let's see, what is the date? 13 October. Basically, if you've got some kind of a differential equation, if you've got a first order differential equation, I think basically we'll find out that we can basically solve them. For second order differential equations, then the Runge-Kutta is a way of numerically integrating a second order differential equation. And I actually don't know how it works, but it presumably is you simply discretize your space, and in other words, you have a step size between x and x plus delta x, and you also specify a range, say 0 to L. You divide this up into n segments. So x1, x2, and xn. Well, I should.
Okay, Hill.
Yeah.
We can't see the board right now.
Sorry.
It's all right.
Oh yeah, I really screwed up there. File, new movie recording, iPad. Okay, so we'll say xk is equal to k over n times L. And so we have, and then the last point is xn equal to L and x0 equal to 0. And so what you have is you have presumably an initial condition, namely f of 0 and f prime of 0. And then your differential equation gives you f double prime at 0 is some big function f of f0 and f prime of 0. So that would be how you'd start. And then once you have those three things, you can approximate f of x1. So this is, you do a Taylor series, you'd say it's f of 0 plus L over n, that's the step size, times f prime of 0 plus a half L over n squared f double prime of 0. And then you continue in this way. Now, this is a straightforward way of doing it that just sort of just follows from first principles. Runge-Kutta is presumably a more sophisticated, clever way of doing it. That, but I would say, I mean, you could certainly Google Runge-Kutta and it would tell us a number of, I mean, that's how I would, so Runge-Kutta methods, Wikipedia, and so this would be a way to, and so you see what they're doing is they're just doing something more sophisticated than what I did. And it's, I don't know, it's pretty technical. I've never actually needed to use Runge-Kutta, so I don't, so as I said, I haven't studied it. So let's switch to, let's have questions that are about the material in the book, and or possibly questions about the homework, although I prefer questions about, you know, that seek further understanding of what the basic concepts are that are explained in the book, or that are, well, directly related to that. So, you know, right on the chat screen, or talk, or, you know, whatever. So I'm really puzzled. No one's asking any questions, and I mean, apart from Runge-Kutta, which, as I said, I don't any. That's certainly fairly technical, and as I said, I haven't worked with it very much, and certainly not recently. What we could do is just go on with some of the material here. The the last thing we were talking about was exact differential equations, and the ODE that leads to Boyle's law is exact because the equation is dPV, and so for constant temperature, dPV is 0, and that's this, and so we just say PV is something, a constant, and that gives us Boyle's law. Another example here is that the number of people rises as the square of the population. I took too big a swallow there. So we can separate this equation. dn over n squared is dt over b. We can integrate, and capital T then is the time when the population becomes infinite. If you set t equal to 2025, which isn't that far in the future, and b equal to 10 to the 11th, it turns out to be a fairly good approximation between the years 1 and 1970. I'm not sure why this example is here, although it's certainly a first order differential equation. Is it exact? I'm not sure whether it's exact or not. Anyway, if you have an equation that, or a system that a first order ordinary differential equation that is exact, then it's of this form, but it's more special than that, because if we just have this form, then we can integrate from x0 and y0 to xy along a contour C, and then we get a function that is a function of fy that then unfortunately depends upon the contour as well as the endpoints. But if this thing is exact, then p dx plus q dy is equal to the differential of something. And so this contour integral is actually just an integral of d phi. And so it's phi of x, phi of xy minus phi of x0, y0. And that then gives us a solution of the differential equation. So an ODE and its exactness leads to an equation of the form phi xy x0 y0 equal to some constant b that one can then solve, and then you say, and then that's a solution because d phi is db equals 0. Here's an example that's probably useful. This thing always is in the wrong place. Suppose we do have an exact equation, exact system. So P is the gradient, the x derivative of some function phi, and Q is the y derivative. Then we have an exact differential equation, and we can use the first criterion that P is the x derivative of phi to write phi as an integral of P in the x direction, which we can do, and we get a function R that we know. But then we have to add in an arbitrary function C of y. But the second criterion is that the y derivative of phi, which will be the y derivative of R, which we know, plus the y derivative of c, which is unknown. But we can find c by then integrating. We can set c, the y derivative of c to be q minus the y derivative of r. And we integrate that and we get just an arbitrary constant d. And now we can put c into the formula. Phi is r plus c, which is this equation. We set phi equal to a constant, and then we get an equation that we can solve for y, namely phi of xy is r plus c, and that's r plus the integral of q minus r minus the y derivative of r plus a constant is equal to e. So this is an equation, this right-hand side is an equation that we can solve for y of x. Here's an example of functions p and q. Here are, in this case, they're factorized. In fact, both are p and q are just a function, no, they're not just functions of y, but they're kind of factorized. And what we've got then is that p is this thing here. The y derivative of p is 2y over y squared plus 1. This is q. The x derivative of q is the same thing. So this is an exact system, an exact first order differential equation. If we follow the same recipe, we integrate first in the x direction, add a function c of y. We then differentiate and we get that, and then we arrive at this expression and we get finally an answer. I think it's best to, if you just work through that on your own rather than that I repeat each of the steps. One thing that's that helps is that you might find an integrating factor that makes your differential equation exact. And so that means that you find some alpha such that alpha p dx plus alpha q dy is the differential of something. And then the thing is exact and integrable. And so what's the situation? Alpha p is the x derivative of phi, alpha q is the y derivative of phi. And so the y derivative of alpha p is phi x, is the double derivative of phi, and that is then the x derivative of alpha q. And as I said, if you can find such an alpha, then you're home free. So here's an example. It's a trivial example. You have an ODE y dx plus minus x dy equals 0. It's not exact, but if you let alpha, you multiply by 1 over x squared, you then get this expression. And now p is minus y over x squared, q is 1 over x, and py is minus 1 over x squared, qx is minus 1 over x squared. So now we're exact. But that's not the only integrating factor. 1 over xy is an integrating factor. And that makes things even simpler because it separates the variables and we can integrate immediately. So what we've learned here is that integrating factors make systems exact, but the integrating factor, there may be several integrating factors for a given system. That's what I said to you earlier about differential equations. They're just all kinds of surprises, and things are not related to each other in the organized way that one finds in complex variable theory. Here's a concept that's important and important in physics, namely the idea of a homogeneous function. So here's a function f of x of k variables, and it's homogeneous of degree n if f of tx, in other words, you multiply each of the independent variables by t, and that's the same thing as t to the n times f of x. So that's homogeneous of degree n because there's an n here. If n were 1, it'd be homogeneous of degree 1. Z squared log of x over y is homogeneous of degree 2. The t's cancel inside the log, but you get a t squared from z squared. And if you have something that's homogeneous of degree n and differentiate, what you get is that d dt is, of course, the derivative with respect to each of the variables, txi, and then that's the derivative of txi with respect to t, that's xi. And that is then equal to, if we look at the right-hand side, the t derivative of this is just n t to the n minus 1 f of x. So now we have this little equation here. And if we set t equal to 1, we get this expression, namely if f of x is homogeneous of degree n, then the sum over the xi's of the partial derivatives, in other words, sort of x dotted into gradient, gives you n times f. So in other words, another way of saying this is x, where x needn't be a 3 vector, it can be an n vector, n dot grad f is equal to nf. So this is one of Euler's theorems, and this has many examples. And since this is a physics department as opposed to a math department, I think, and since this is a problem session as opposed to a 466 class, this is a 466 problem session, I'm going to go through some of these examples, namely the internal energy is a first degree homogeneous function of the entropy, the volume, and the number of molecules of kind J. And that's because if you scale up all of them, the internal energy just increases by the factor of T. And that's because the internal energy, if you say double the system, well, you have twice the entropy, twice the volume, twice the number of particles, and so you have twice as much energy. So it's homogeneous of degree 1, or first degree homogeneous. The temperature, pressure, chemical potential are defined in this way. And so the change in the internal energy is du is TdS minus PDV plus these the chemical potential mu J's times the change in the number of particles. And Euler's theorem then tells us that we can express the internal energy for n equals 1, then it's just the variables T minus P and the mu's dotted into, or rather it's SV and the n's dotted into the partial derivatives being T, P, T minus P and the mu's are the partial derivatives. So this thing is U is equal to here partial U partial S, that's T times S plus partial U partial V, that's minus P times V plus sum on J, partial U partial Nj times Nj. So that's what we can rewrite this equation as, and when we rewrite it this way, then it looks like this. If the energy density of empty space is positive, then the internal energy rises as it expands. So that just stands to reason. On the other hand, the definition of pressure is that is the derivative of the internal energy with respect to volume. Well, if this is positive, then the pressure is negative. And that's the picture that we have of the universe now, namely that it's expanding and it's accelerating due to negative pressure. And the most popular theory of the very early universe, and here we're talking fractions of a second, not the first 3 minutes, is that there was a period in which the negative pressure was enormous. In other words, the energy density of empty space was enormous, was briefly enormous, and there was then a superluminal expansion of the very early universe, and we call that inflation. So this is basically what we had before. So let's just look back at that. This equation, then we can rewrite as du over t plus p over t dv minus all that, which leads to these relations that 1 over t is the derivative of s with respect to u, and p over t is the derivative of the entropy with respect to volume, and derivative of the entropy with respect to number is minus mu j over t. On the other hand, the entropy is not a homogeneous function of the internal energy, the volume, and the number of particles. What one can derive is a formula for the entropy of an ideal gas. And so now we see that the entropy here is a rather complicated function of u, v, and n. And if you multiply u, v, and n by t, well, here there's a cancellation, but this thing didn't get, oh, here and there, here there's also a cancellation. And then there's a factor out here. Boy, that almost looks homogeneous of degree 1. See, we have U, N, and V. Well, the entropy is presumably not in general homogeneous, but in this particular case, it looks to me to be homogeneous, unless I'm missing something. Does some student see what I'm missing? Okay, so I'm going to have to look at this in more detail and change. This is actually an error then. So let me just say to myself, look at 7.121, because that could be, the equation I think is right, but the comment before it could be wrong. But let's now apply this notion of homogeneity. And one of probably the most important application is to the Virial theorem. If you've got n particles moving non-relativistically in a potential of 3n variables that's homogeneous to degree n, say. Well, the virial is defined as this thing. It's basically x dot p. So you say here that G is the virial, and it's basically x dot p. And x dot p is something that occurs all over the place in physics. Now, in terms of the non-relativistic energy, kinetic energy, that's T is V dot P over 2. And the force, of course, is P dot. And so the time derivative of the virial is, well, you differentiate with respect to time, you get V's here and you get forces there. And so you get twice, well, then VI PI is, V dot P is 2T, and then, so you get 2T plus X dot F. And now if you take a time average of this, and here the idea is you have an infinite time average. So and you imagine that the virial is bounded. And so what you're imagining then is that there's a potential here that keeps the n particles in a finite region of space. And in the sense, when I said space, I should have said phase space, namely that we want to say that G is bounded as time goes by. And since G is bounded and we take the limit 1 over T times delta G, we get 0. And so that tells us then that 2T plus this is 0. And so that gives us a formula here, that 2T plus X dot F averaged. The time average of that is 0. And now, in the case of Newton's law, the F's are partial V, partial Xi, and so that is the time average of the kinetic energy is X dot, the time average of the gradient of the potential. And so the thing is, and this is time average, so time average is equal to the time average of a half sum. Well, never mind the sum, so let me get rid of time average of X dot grad V. And so far we've just been deriving something in general, but now if V is homogeneous of degree n, then you have that grad V that Euler's theorem, which was way back here, we would have X dot grad V would be NV. That's Euler's theorem. And so if we come back to the Virial theorem, we have that the average value of T then is N over 2, times the average value of V. So this then is the virial, a sort of general virial theorem. So this is called the Virial Theorem. And what does it require? It requires that V be homogeneous of degree n. And we're treating things non-relativistically, and that motion in phase space is bounded. But in many, many cases of interest, that's true. So for example, if you have a gravitational or an electrostatic potential, you are homogeneous of degree -1, because 1 over TR is 1 over TR, or it's equal to T to the power -1 times 1 over R, sorry, 1 over R. Let's see, I should probably redo this because it looks kind of silly. So there you've got n equals -1. And what does this tell us? Well, this tells us that the mean value of the kinetic energy is equal to -1 over 2 times the mean value of the potential energy. And if we look at an electron in hydrogen, then the actual energy approximately is minus, this is a very nice formula, by the way, it's minus mc squared times alpha squared. In fact, the actual energy levels are minus mc squared alpha squared over n squared. These are the energy levels. For the ground state, you have n equals 1, which is here, and alpha is E squared over H bar C, which is roughly 1 over 137. And so that's the total energy. That is then T plus V. And now since T is minus a half V, you see that E is equal to a half V, which says that the potential energy is basically minus around 27 electron volts. And the kinetic energy then is 13.6 electron volts. And that pulls you up to a total energy of, oh, there should be a minus sign here. So that's after 7.129. Well, let me fix this really quickly. This is just pretty easy to fix. So that's obviously a minus sign. Back in the 30s, and now we're talking 90 years ago, almost 88 years ago, Zwicky, a German physicist or astronomer actually, applied the Virial Theorem, a gravitational version of the Virial Theorem, and still you have n equals -1, to the galaxies of the Coma cluster, a cluster of galaxies. And he used his observations of their luminosities to estimate the gravitational term and found it to be much less than their mean kinetic energy. And so what he said was there must be some transparent matter there, matter that he couldn't see. And he called it dark matter. But if he had thought a little more carefully, he would have called it transparent matter, because what he would have seen was that the coma cluster, if it had been dark matter, if the missing mass had been dark matter, or I should say the invisible mass had been dark matter, then that dark matter would have blocked the stars, the light from stars coming beyond the coma cluster. And so this matter that's called dark matter is actually transparent or invisible. And from the physical point of view, it's just that it's, you could say it's simply neutral. If it's uncharged, it doesn't interact with photons, and if it doesn't interact with photons, then we don't see it. Of course, you might say, well, we see a neutral piece of wood. Well, but a piece of wood is not microscopically neutral. It's made of atoms and molecules, and these atoms and molecules have charge, have electrons whipping around like crazy. So that's the situation. Now, another example is harmonic forces, where the potential goes as r squared. That's homogeneous of degree 2. And so the long-term time average is that the kinetic energies are simply equal to the potential energy. And so let's see, I've been going on now for some time. I don't see anything written in chat, and I don't hear a question. I could just keep going. By the way, I put the new homework I put 2 new homework assignments, mainly focusing on the last half of complex variable theory and the first part of the differential equation chapter. I put that on the class website. Also, yesterday's class, there wasn't any student participation in yesterday's class, so the FERPA rules don't apply. So I just I made it public on YouTube, and I'll send you the link. So let's see. Well, Legendre's transform, I guess we have time to do that. This is, again, something terribly important in physics. And in fact, when you're taking a physics course or reading a physics book, the teacher or the author will assume you know about Legendre transform and just do it. And if you haven't seen it, then you're in trouble. So let me try to explain these. So suppose you got a function of 2 variables, x and y, then dA is partial a partial x dx plus partial a partial y dy. Now you can define a new variable v as this derivative. And that might, if you do that, that might be, you might say that's asking for trouble. And you could define a new function b as a minus vy. So now you say, well, we've really screwed things up. But what's the change in b? Well, the change in b is going to be, well, b is a minus vy. So it's partial a partial x dx, but partial a partial y dy, minus dv times y. And on the other hand, there's a cancellation here. The cancellation is that here we have, from this term, we have partial a partial y dy. then the first term here is dv times y, but the second term is the partial of the second term is v times y, and v is partial a partial y. I'm sorry, times dy. And now you see this one cancels that one. And so what you're left with is the first one and this one in the middle. So it's partial a partial x dx minus y dv. And so b, now we see what is b? Well, changes in b are proportional to dx and dv. So b is actually a function of x and v. And so in other words, we can write b as a function of x and v, but in order to do that, we have to express y as a function of x and v. And so that means we have to take this equation and invert it so that we can express y as a function of x and v. Now, in simple cases, one can do this, and in other cases, one can't. And so it's not, this Legendre transform thing doesn't work all the time. And the time in which it works most frequently, I think I'll just jump to that, is when you start out with Lagrangian, and you say, well, dl is partial L partial Q dq plus partial L partial Q dot dq dot. That's because, so let me switch to blue here. So a Lagrangian is a function of Q and Q dot, and in general, it's a function of a bunch of Q's and a bunch of Qi dots, and it could even have a time in there. And when the time is in there explicitly, then energy typically is not conserved. And so we prefer the case where T does not appear. And so let's just look at this simple case. And what one does, of course, in physics is we define P as partial L partial Q dot. And then we say, well, the Hamiltonian is P Q dot minus L. And that means then the DH is what? Well, it's P dQ dot plus Q dot dP minus dL. But now, let me get rid of this damn thing and this. And now what's dL? Well, this is then P dQ dot plus Q dot dP minus dL. Well, dL is partial L partial Q dQ, partial L partial Q dot dQ dot. And now we've already said that P was partial L partial Q dot. So these two terms cancel. And what we get is the DH is Q dot dP minus partial L partial Q dQ. So H is a function of Q and P, and that's what we call the Hamiltonian. And the overall minus sign, by the way, in here is to make H positive in most cases. But in order to do this, we have to be able to express P. So we need to say, we need to express Q dot as Q dot of Q and P, because what we have is we have H defined in terms of a Q dot here, and this is L of Q and Q dot. And so we've got another Q dot here. And so we have to re-express Q dot in terms of Q and P. Now, in the very simplest cases, L, you see, is equal to a half Q dot squared minus V of Q. And in that case, P, which is partial L partial Q dot, is just Q dot itself. And so the expression of Q dot in terms of P and Q is trivial, and we get that H is equal to what? PQ dot, but that's P squared minus L, so that's P squared minus a half Q dot squared plus V, but Q dot is P, so this is a half P squared plus V. I've set M equal to 1 in this example. So that's the case that occurs almost universally in simple physics problems. But you can have actions that are not simply quadratic in the time derivatives of the coordinates. And in that case, the Hamiltonian's not so obvious a quantity. Let me see if I can. Oh, it went away. Okay. All right. Well, we're out of time, and I haven't seen any recent questions. So I'll just wish you all a happy fall break. There's no class tomorrow, and there's no class Friday, no colloquium. So just, look both ways when crossing streets. I'm always amazed at the number of people killed in traffic accidents. So remember that cars are dangerous. And in fact, these days, cars are more dangerous than they used to be. We have seat belts and we have airbags. So the people in the vehicles, modern vehicles, are safer, but the modern vehicles are huge. The pickup trucks get bigger and heavier. The SUVs get bigger and heavier. And some of the other, these various hybrid forms of cars and trucks, they're all really trucks. They're getting heavier and heavier, and so they're doing a great deal of damage. The death rate on highways has gone up, and the pedestrian death rate has gone up. So watch out for these huge vehicles. Look both ways crossing streets. All right, so I'm going to say goodbye now.